Hey everybody, here's tutorial 4, part 2a. We're going to look at a bunch of things in here. First of all, I want to look at the erase color attribute of jit.world. As you can see, we have a white background here. That's because the erase color is set to 1111. The 4 arguments to erase color are the color, red, green, blue, and then the 4th argument is the transparency, or the amount of the image that's erased each frame. So 1 means 100% of the image is erased each frame. Lowering this value will give us trails, which we'll take a look at in a moment. If I want to, for instance, erase my world to red, I can do erase color 1001, which will give me a red background, and then set it back to white with erase color 1111. So I want to revisit using sine and cosine to move in cyclical patterns, sine and cosine. And with sine and cosine, you can take any linear value that's changing, like for instance the elapsed time here coming out of the snapshot, and it will become a cyclical value. Pack the result of sine and cosine together. Use them to drive the position of our grid shape. Zoom out a bit and we can see our shape is now moving in a circle. But there's a couple of interesting features of sine and cosine that we haven't discussed yet. Before we do that, I just want to use this alpha attribute of the erase color so that we can see trails on our object. If I set my alpha value to 0.5, only 50% of the image is erased each frame, which means there's some residue there. There's a trail. If I make this even more extreme, like 0.2, then only 20% of the image is erased each frame, and I get a nice persistent trail that allows me to see what's happening with this object. I could even take it down to 0.15 to get an even longer trail on the object. So when we're dealing with sine and cosine, of course we can get a circle out of it, and that's very nice, but we can also get a lot of other curved shapes, and that's done with just a little bit of math. If we multiply before our objects, we're changing the frequency of the oscillation. So I've made multiply by 0. Now you might think it's a little odd. Why multiply by 0? Well, it's because I want to show you what the right inlet of math objects does. So multiplying anything by 0 gives you 0. So this time is actually, if we put a number box here, this time is actually being erased. 0's coming out. But if I put a number box into the right inlet, I can now change this 0 to another value. So for instance, if I put in 1s, it's moving in the circle again. Now notice the argument doesn't visibly change. These 0s have been replaced by these 1s, but the 0s will still display inside the math objects because these are also our defaults that'll be restored when we save and close the patch. So what do I mean by frequency? I mean how often this cycle repeats. So right now the sine and the cosine are repeating at the same frequency, so we see a circle. But if, for instance, I increase the frequency of the x, right, the x is changing twice as fast as the y, so it's no longer a circle, it's now a Lissajous pattern. If I go to 2 by 2, it's a circle again because they're changing at the same rate. If I go 2 by 3, now the y is changing faster than the x. So again, we get a non-circular pattern again. And these are going to give you repeating patterns as long as these are in an integer relationship. But if you begin to use the floating point aspect of them, you're going to get a non-repeating pattern, or a pattern that doesn't repeat anywhere near as frequently, anywhere near as often. So frequency is a function of the input to sine and cosine. Amplitude, or scale, is a function of the output of sine and cosine. So if we take these and do math on them, I can do a little encapsulation here to tidy this up a bit. I can encapsulate here too. So what I mean by amplitude is how large is the oscillation. So right now, I'll put it back to a circular rotation. Right? Everything is ones. But if I change the amplitude, for instance, make the y amplitude 0.5, notice I've got an oval now. It's only moving vertically in the y half as much as it's moving on the x. If I restore that, it moves in a full circle again. Here I've got another object that I can turn on so that we can see this movement in relation to something else. So for instance, here is a Earth, if you will, and now I've got a moon orbiting around it. So let me change the orientation here. I'm going to de-encapsulate these so that we can get back at the whole mess here. And I'm going to change my rotation to be x and z, which is what we've been working with so far. So now we're looking sideways on the orbit of this red moon around the blue sphere. And you'll notice that the nice trails that we have, they're not showing when we're interacting with the blue sphere, and that's something we can address later, but for now, let's just live with that. Because what I really want to talk more about is the motion. Because what's happening in y? Well, at the moment, nothing is happening in y. We can certainly put a value into y just by attaching a number box here and raise our moon up so it's orbiting in a high orbit, or take our moon down so it's orbiting in a low orbit. And these are sort of unrealistic from a an actual physics perspective. A moon wouldn't orbit like this. But we can also take our sine, and we can actually take the entire structure here and pass it into the y. And now we have the possibility of a diagonal orbit. And what's also interesting is by changing the frequency of our new y variation, we can have a spiral orbit. Here's a spiral. It's changing its y 1/4 as fast as it's changing x and z. Maybe this is better now as a cylinder. There's a tall cylinder, so we can see the red ball is corkscrewing around it because it's moving in the x, y, and the z dimension. So let's say that we want our ball to change color when it's on one side or the other of the cylinder. So we'll say when it's to the right of the cylinder, when its x is greater than 0, it'll be white, and when it's to the left of the cylinder, it'll be red. So this is what togedge is all about, right? It takes a conditional, like greater than 0, and says when the condition is met, do one thing, and when the condition is not met, do another thing. So when the condition is met, when the x position is greater than 0, we'll change it white. But notice that it stays white. So if we want to change back, we're going to have to say, when the condition is no longer met, change it back to red. Right? It's red when it's on the left and white when it's on the right. So that's togedge. It's looking for the edge transition of when the value becomes greater than 0. If we just want something simpler, that's a Boolean operation, a 1 and 0 operation, we actually don't need togedge. We can use the object change. So for instance, if we want the column to be only enabled when the ball is on the top half, we could say when the y is greater than 0, when this changes, enable it. So now the column will exist, and then when the ball drops below y equals 0, the column disappears, and then the column reappears. And the column disappears. Now, why does this work? This works because the greater than 0 outputs a Boolean response. It outputs a 1 if it's true and 0 if it's false. So as a last thing, I just want to look at gate again, because gate allows information to pass or not pass based on the value that's sent to its left inlet. So exactly the same thing here. As our circle rises above y0, the gate opens, right? If greater than 0 is true, a 1 will be sent to the gate, opening the gate. Now what's going through the gate? Nothing at the moment, but we can take a value and pass it through the gate. So for instance, we can take the y value and map it to the scale of the cylinder, only when the gate is open. So only when the ball is on the top half. So here it's normal, but when this condition is met, the scale of the cylinder is equal to what's coming out of this cosine. We can divide this a little bit to make it less dramatic. Right, so why is this pulsating again? This is pulsating because when the y position is greater than 0, meaning when the ball is above the midline, the gate is opened. And when the gate is opened, the value that's coming out of the cosine here, divided by 2, is passed to the scale of the cylinder. Or if you prefer, it could be passed to the scale of the ball itself. So the ball is at a fixed size when it's below center. There, it's not changing size. And then it's at a variable size when it's above center. We could do further division here so that it doesn't get so big.